Welcome to Section 3. In previous sections we've used a number of pre-trained models and algorithms to develop our solutions. In this section we'll be tackling a much harder problem of predicting taxi journey times, and we'll build our own model in the process. In this section we'll cover a summary of the problem, how we'll approach it, we'll look at our environment and our data set, we'll explore our data to see what it tells us, and then we'll train our model and we'll test its performance. Let's start with a summary of the problem. We see this use case in many areas. Most notably, those that use Uber will see that they try to predict how long it will take for an Uber to reach you, and also how long the journey will take. In most situations, they provide a range of times as the conditions on the road are always varying and inherently impossible to predict. If we assume we have a data set of historic taxi journeys, we will know the pick-up and drop-off locations and times, the fares, the distance of the journey, etc. It may also be possible to get a reasonable approximation of the weather conditions too. However, it may be that drivers take different routes based on their local knowledge, or because something is happening at that moment on the road. For example, an accident, a build-up of traffic, the lights change at a certain moment, a truck reverses from a side road, etc. No dataset could ever hope to cover all of these situations for every single trip, so we are therefore unlikely to build a perfect model. What we can achieve, though, is to take these factors and create a model that gives a reasonable approximation of the journey times between different locations. And that's what we'll do in this section. So how will we approach this problem? We'll start by using open data provided by New York City. They provide both taxi journey and weather data going back many years. Using this data, we'll develop features that enrich the data and thereby enhance a model's ability to learn. And then we'll build a neural network that learns from this data in order to predict subsequent journeys. It's worth stating that this model requires a powerful PC with a GPU, or use of a cloud-based GPU instance. The dataset is large and needs at least 8 GB of memory to process. As mentioned previously in this course, I used a Google Cloud instance with 2 cores, 13 GB of memory, and about 100 GB of disk space, connected to an NVIDIA K80 GPU. Even with this processing power, this model took about 8 hours to process. Also, please check Python version compatibility with TensorFlow. At the point of writing this course, TensorFlow version 1.11 was only compatible with Python version 3.6 and not the most recent version 3.7. If you want to have a look at the full dataset, there's a link here to the nyc.gov website. For those of you unfamiliar with the map of New York City, the link at the top of this slide will show you New York City on Google Maps. We're going to work with the June 2018 data for this section, and the relevant data sets are included in the repo with the code.